Okay, let's talk about conservation momentum. So conservation momentum, the definition is for any collision or actually any event, the sum of momentum before any event is equal to the sum of momentum after the event provided no external resultant force acts on it. So what does it mean? That means if you don't want to use collision also, can you just say in an isolated system? In an isolated system, the sum of momentum before any event is equal to the sum of momentum after the event provided no external resultant force acts on it. Now, isolated system has the same meaning as no external resultant force. Understand? So that means isolated system implies that let's say you have a car colliding with a van, then all the forces are between the car and the van. That's it. If there's friction at the road or air resistance, all these will be external forces. So your momentum is only conserved if you ignore or there's no other external resultant force acting. That means there can be no friction with the road, there can be no air resistance, then only your momentum is conserved. You understand? Okay? So generally, there are few types of event that we're going to learn. First one will be collisions. So collisions will have altogether 3 types of collision. First one is called elastic collision, or some people call it perfectly elastic collision. So in physics, right, if you see elastic or perfectly elastic collision, they are the same, which implies that they must separate after collision, and most importantly, your KE is conserved. But I won't mention about momentum because momentum is always conserved in whatever event. So whether it's elastic, inelastic, perfectly elastic collisions, or explosion or implosion, your momentum must always be conserved in an isolated system. So we are only talking about the differences on it. So in elastic, also called perfectly elastic collision, it must separate after collision, but most importantly, your KE must be conserved. When I say KE is conserved, I'm talking about total KE before and after the collision must be conserved. For inelastic collision, it means that it also separates after collision. That means if we look at a collision and the objects separate after collision, we cannot conclude straight away that it's elastic or perfectly elastic, because it can also be inelastic, because inelastic means also separating. But the difference between inelastic and elastic is, in inelastic, your KE is not conserved. That means if you total the KE before the collision, you will notice that it will be more than the total KE after collision. Some of the KE will be lost, definitely, but definitely not gained. It will be lost after collision. But when you use the word perfectly inelastic collision, that means what will happen is that it will definitely stick together after collision. Okay, that is perfectly inelastic. Okay, so don't forget, perfectly inelastic stick together, inelastic and elastic separate. Okay, now then we have explosion. So explosion would be when the object is initially at rest, suddenly it splits. So example would be like nuclear decay, or you shoot a bullet out of a gun, or you shoot a cannonball out of a cannon. So initially they rest, then they move in opposite directions. So that's called explosion. But you can also apply it to like implosion. That means, for example, you pull 2 trolleys apart, attached to a spring. That means, let's say there's a spring connecting 2 trolleys, and then you pull them apart. When you let go, they'll come back, right? So that will be moving towards each other. Alright? So that one, also your initial momentum is 0. Because when you hold them apart, they are stationary, so their initial momentum is 0. So therefore, when you let go, they must move in opposite directions with equal and opposite momentums, so that when you add up, you will get 0. Explosion also same, initially is stationary, so the momentum is 0. So when they explode, they must move in opposite directions with equal momentum as well. So when you sum them up, it's also equal to 0. Do you understand now? So these are your main events that we're going to talk about. Okay? Now, for equations wise, okay, let's look at the collisions first. For elastic collision, so what I've shown you is the objects. I'm assuming that initially they're both moving to the right. After collision, also moving to the right. Because momentum, is it a vector or scalar quantity? So vector quantity means direction is important. So I'm going to take to the right as my sign convention. It means right is positive. So let's say if the object both moving to the right, so the total momentum before collision, isn't it m1 times u1 plus m2 times u2? Agree? So that's the total momentum before collision. And it will definitely be equals to total momentum after collision, so you get m1 times v1 plus m2 times v2. So that's conservation momentum. If any one of these objects is moving to the left, you must replace with a negative momentum. Do you understand? Direction is important. Example, if this one moving to the right, this one moving to the left, then it will be m1 u1 minus m2 u2. Okay, that's how you use the equation. Now, because this is an elastic or perfectly elastic collision, you can also use conservation of kinetic energy. That means conservation of kinetic energy, COKE. So half m1 u1 squared plus half m2 u2 squared must be equals to half m1 v1 squared plus half m2 v2 squared. Agree now? Now, this equation is a little bit more tedious because there's a square there. So there's a way to simplify. If you were to solve this conservation of momentum and conservation of kinetic energy simultaneously, you can solve a simultaneous equation, you will get this equation, which is velocity of approach equals to velocity of separation. Now, you don't have to prove it or derive it in your syllabus, but if you're interested to, you can see in the next page, there's a derivation there. What's important is how you use them on it. How you use is you get u1 minus u2 equals to v2 minus v1. So what does it mean? Now, remember, all the equations that you see here are based on this diagram. And what does the diagram show you? The diagram shows you that all of them are moving to the right. So when you have u1 minus u2, it means that if both of them are moving to the right, then you use this straight away. For example, let's say u1 is 5 to the right, u2 is 3 to the right. Both to the right, then you use 5 minus 3. But if let's say u1 is 5 to the right, but u2 is 3 to the left, then you must take 5 minus negative 3. That's how you use it. Similarly, equals to v2 minus v1, also implying both moving to the right. If let's say v2 is 3 to the right and v1 is 1 to the right, then it is 3 minus 1. But if let's say your v2 is 3 to the right but v1 is 1 to the left, then it must be 3 minus negative 1. That's how you must use the formula. Understand? And the formula is u1 minus u2 equals to v2 minus v1. There's no mistake. Some people ask me, shouldn't it be 1 minus 2 equals to 1 minus 2? No. When you derive the equation, you notice the sequence is correct. It's u1 minus u2 equals to v2 minus v1. You must remember this sequence. Understand? So that's how you use elastic collision equations. But for inelastic collision, it separates after collision, but there's no conservation of KE. That means you only use the conservation of momentum, which is the same as elastic collision, same equation. But for perfectly inelastic collision, then we can use slightly different because they stick together, so they have a common speed. So your conservation of momentum would be m1 u1 plus m2 u2 equals to, you add up together, m1 plus m2 times a common speed v. Understand? Now, as for explosion or implosion, same, because when you separate from rest or you join together and come to rest, your equation is a total initial momentum must be equal to total final momentum also, because conservation momentum. So your equation will be 0 equals to m1 v1 minus m2 v2. Why? Because they're moving in opposite direction. That's why one I put as positive velocity, one I put as negative velocity. So your momentum, one is positive, one is negative. Understand that? Now, a very good example of implosion. Right? Well, remember I was telling you, if let's say you had a trolley attached to a spring, attached to another trolley with using a spring, and you pull them apart. Okay, you pull them apart, you hold them apart. When you let go, they'll move towards each other, right now? Now, assuming that both trolleys have different masses, let's say A is heavier than B, and you hold them apart. When you let go, they'll move towards each other. When they hit each other, right, will they stop? They will stop. No matter if they're different masses. You know why? When you're holding them apart, what is your total initial momentum? So when they're moving, the total momentum must also be 0. When they hit each other, total momentum must also be, so they must stop. there's something unusual because it's conservation of momentum. Do you understand? Okay?